introduce the team before we present. So I'm Trevor Burke from Dallas, Texas.
Hi, I'm Lisa Alexander from Houston, Texas.
I'm Braxton Hornbuckle from McAllen, Texas.
I'm Jaden Wood from Murrieta, California.
I'm Lauren Rodriguez, also from McAllen, Texas.
I'm Sarah Smith from Des Moines, Iowa.
I'm Rajuka Karlafudi from Overland Park, Kansas, and this is the Lunar Orbiting Volatile Experiment Satellite, aka LoveSat.
Alright, so our mission was to design a system, a concept of systems for a 6-unit CubeSat to orbit the moon and measure and map volatiles on the moon. A CubeSat is a small 10-centimeter cube of a satellite. This is a full-scale model of such a cube. For our satellite, our LoveSat, we got 6 of these CubeSats that were all interconnected to form one larger satellite. Right here is a full-scale mock-up of a CubeSat with the solar panels deployed. And so we don't have a lot of space with our CubeSat to measure volatiles. And the volatiles we're measuring is any sort of gas with a very low boiling point. And so it's practically a gas on the moon. And so we had to have a number of concept designs in order to make our satellite be able to accurately map the volatiles on the moon.
So before our group began designing our CubeSat, NASA Ames provided us with a number of constraints. These requirements guided our research as we explored different ways to map the lunar surface. For example, one of these requirements was that the total power of our payload was 10 watts. The requirements also restricted the size of our payload to 4 units of our total 6-unit CubeSat, with a mass of no more than 5 kilograms. Again, the goal of our mission is to confirm the presence, map the concentration, and plot the density of a wide array of volatiles on the lunar south pole.
Now, our CUBE satellite is based off of several driving assumptions. First and foremost, our CubeSat, LoveSat, is based off of NASA Ames BioSentinel. So we are resting on the assumption that BioSentinel meets the specifications for a 6U CubeSat. We are also assuming that NASA Ames has provided us with 2 gigabytes of storage. We are assuming that our lunar orbit will be stable for about 15 days, which is just enough for our nominal mission. And finally, we are assuming that we will have access to a 12-meter satellite dish for at least 1 hour per day. So throughout the project, me and Jaden made extensive use of CAD software, specifically Autodesk Inventor. With our CAD model up here, we were able to visualize the geometry of our CubeSat and, more importantly, using the mint-array renderer, see how light reflects and bounces off the solar panels. Right here, you can see our CAD model in its completed state.
As Trevor previously mentioned, our satellite is composed of 6 10-centimeter unit cubes, and 4 of those units are allotted for our instruments, the 2 instruments that we chose, which will sense the lunar volatiles. So the 30 by 10 by 20 centimeter body of LoveSat holds the 2 instruments in the front 4 units of our satellite, while the back 2 units are allotted for the rest of the systems that NASA Ames is providing us. The structure of the 6-unit body is made of aluminum, as well as the panels on the outside that shield the structure of our satellite. The 4 solar panels are mounted on the front of our body of the LoveSat so that the solar panels will constantly face the sun to power the satellite for our mission. Now Braxton will discuss the internal and external features of our satellite.
So right here on this CAD model, you can see on the exploded view, that square right there, that would be Birch's. That is our IR spectrometer. And next to it is our Chameleon Imager, which is our camera. You can see on the top panel right there, which will be facing towards the towards the moon. It has been machined through and designed so that these instruments can face outward. Also, we have a medium gain antenna, which has been modified by Lauren and Raju, which is broadcasting on X-band. This antenna is also directable in 3 dimensions, so that we can always keep in contact as much as possible with mission control, as well as transmit and receive data.
For our mission, we selected the lunar South Pole as our region of observation. We know already that volatiles are present here, so now our task is just to identify which ones are specifically present, pinpoint their exact locations, and report the density of these materials. The region we will be observing is 1,250 kilometers in diameter, and it receives no sunlight. For us, this is a good sign because this means we have shadowed craters that are full of ice, cold traps that have hydrogen and volatiles, and even fossil records of our early solar system. We did consider collecting data at both the north and south poles of the lunar surface. However, previous sensing missions and data that we do know lets us know that the South Pole has a lot more potential for volatile exploration than does the North. So rather than sensing twice per orbit, we're going to save our battery and maximize data collection at just the South Pole. So to do this, and to allow for constant communication with Earth and recharge for our power systems, we have a slightly elliptical orbit selected. Its period is about 164 minutes per orbit. At the paraloon, we will be collecting our data. The paraloon is, in this case, the South Pole. We'll be traveling at this point at 1.78 kilometers per second, and we will be at an altitude of 100 kilometers. We will be sensing for a total of 11.7 minutes, which takes just 7% of our orbit. So for the remaining 152 minutes of our orbit, our CubeSat will be moving a little bit slower so that we have time to recharge our battery systems using solar panels and transmit our data back to Earth safely. At the apolloon, our LoveSat will be traveling at its slowest point at 1.2 kilometers per second, and it will be at 1,000 kilometers in altitude. So as you see that little chart right there, it's a lot closer at the bottom at the paraloon than it is at the top. So it goes faster at the bottom, and that helps us conserve energy because we're only sensing for as long as we need to before slowing it back down to transmit everything back to Earth. So looking at our mission as a whole, we have 4 phases in our mission. First, we have launch. NASA Ames will be planning and launching our satellite for us, so we are going to just assume that we will be placed into the orbit that I just discussed, and that it will be in a stable state so that we don't have to worry about immediate realignment or orientation shifts. Nothing will be powered on until we get to the initialization phase. Here, we will turn on the power of all of our systems, we will be deploying our solar arrays, and we will be making sure that all of our systems are functional and that we have signal back to Earth. Next is our 10 days of planned operations. This is most easily divided into the 2 sections I just discussed, of data collection and transmission and recharge. We estimate that we will get 100 orbits out of our CubeSat in these 10 days, which totals to about 19.5 hours of data collection. Beyond this point, we will be doing nothing to decommission our satellite from its orbit or from its functionalities, because there is a chance that it continues to function. In this chance, we'll be placing our CubeSat in an alternate concept of operations, in which it will be collecting data at every South Pole pass, and it will only be downlinking the data back to Earth when the antenna and the receiver site align. Eventually, when systems inevitably do fail, our CubeSat will either crash into the moon itself or experience orbital decay and become space debris. Given the very, very small size of our CubeSat, either of these options is acceptable. Ultimately, so long as we receive 10 functional days of data, we have a successful mission.
So after looking at the orbit, what we have to consider is the orientation of the satellite in this orbit. Now, the main considerations you have to make for this is where the solar panels are facing and how the instruments are also pointed. In consideration to the solar panels, we had to discover the optimal orientation for energy production. Now, we found that this was when the panels were faced perpendicular to the Earth-Sun line, essentially meaning we're facing the sun the entire time. This is because the LoveSat recharge period is essential for the instrument's sensing abilities, and that means that we're able to get that's because we have to get the optimal exposure and thus get the most efficient data collection from our power. This is also the reason why we chose the full moon phase for our mission, because we're able to get that full exposure. Now, to maintain this satellite orientation, LoveSat will move 1 degree per day in order to stay perpendicular to that Earth-Sun line and still continue to face the sun throughout the mission. The other consideration we made was how the instruments were facing during the orbit. Where they face as LoveSat, we had to think about where they face as LoveSat orbits the South Pole, and so we had to think about how efficiently we wanted to collect this data in consideration to where the aperture and lens of Birch's and the Chameleon Imager, our instruments, were facing. They'll be oriented parallel to the surface of the lunar South Pole, and in order to save energy, that's never going to change. So essentially, it'll be facing up the whole time, or parallel to the South Pole. This also means that the 10 by 30 centimeter side is what's going to be facing that surface. This is achieved with the attitude determination controls given to us by NASA Ames in their 2U segment of the satellite, and that allows our instruments to do their jobs. And then after looking at the bigger picture, what we have to look at is the design constraints and the specifications we were given at the beginning of the project. Now, the main 3 constraints we were given were mass, power, and volume. 6 units, what we discovered, is a small amount of space, especially when 2 units is already taken up by NASA Ames. For our payload segment, we were given 5 kilograms of mass, 10 watts of power, and 4 units of volume to work with. The table shows you how we allocated our resources, and Raju will later discuss how we achieved those 10 extra watts of power that you see on there. Most of the telling information that you see up there is in the margin. For a typical mission, what you want to do is use about 60% of your allotted power in order to avoid battery decay, and the good thing is that we managed to use only 53%, but as you can see, volume ended up being the most limiting factor that we were working with, which led to a lot of trial and error with what instruments we chose to use.
NASA Ames is providing the Biosentinel bus to aid our design for volatile sensing. Ames has all the systems that we need to run our instruments for our mission. Starting with the most important system on the bus, the power system, it has solar panels to recharge the battery cells. The power system must provide wattage to run all the instruments and all the systems on the satellite for the duration of our mission. The orientation of our satellite is very important for remote sensing, solar power, and communication. The attitude control system orients LoveSat using a star tracker, reaction wheels, and an IMU, which is an inertial measurement unit. The star tracker measures the position of the stars to determine where we are in space. The reaction wheels enable a precise pointing of the satellite with 4 wheels that will slowly rotate the spacecraft to orient it correctly. And lastly, the IMU, the inertial measurement unit, will measure linear and angular motion for configuration during our sensing period. Now, the communication system between LoveSat and mission control is achieved with an EPS, an electric power system, an iris transponder, a medium gain antenna, and 2 low gain antennas. The EPS, the electric power system, contains a computer and memory storage for data collection, while the iris transponder receives and transmits signals. The medium gain antenna is our main system for transmitting data, while the 2 low gain antennas are only intended for transmission if the medium gain antenna fails to operate. The propulsion system on board the satellite uses cold gas thrusters to orient the medium gain to face the Earth to maintain communication. And lastly, the thermal system that Ames is providing us maintains a working environment between 10 degrees Celsius and 50 degrees Celsius. For the selection of our instruments, it involves the balance between multiple factors, specifically mass, cost, reliability, and power consumption. For remote sensing, there are active and passive sensors, in which active sensors use more power than passive sensors. Active sensors require an external source of power to sense the data, while passive sensors simply just detect the input from the surrounding environments. With the limited power that we have, passive sensors met our constraints. And now Trevor will talk about the instruments that we chose.
All right, so the most critical thing for our sensors is it had to be able to measure the volatiles. The main volatiles that we're measuring was water. Previous studies on the moon have detected that there is water on the moon. However, where it is and how much it is has not been fully determined because the most studies have been done using IR spectrometers only tell elemental form of hydrogen, which leaves it ambiguous to whether it's really water or another compound of hydrogen. And so, for that reason, we chose birches and chameleon in order to measure the water and water-like molecules on the lunar surface itself. With this, we can create an accurate model and understand the thermodynamic history of the moon in a much better way.
So the primary instrument on our CubeSat is birches, or the Broadband Infrared Compact High-Resolution Exploration Spectrometer. Birches is essentially a scaled-down version of OVERS on the OSIRIS-REx, which some of you may recognize as part of the New Horizons mission. Birches, as the name implies, is an infrared spectrometer and can see down to 1 to 4 microns and has a resolution of 10 nanometers. With this, we can distinguish volatiles from our altitude of 100 kilometers. The volatiles that we'll be able to sense with birches will be water, hydrogen sulfide, ammonia, carbon dioxide, methane, hydrogen, hydroxide rather, and mineral bands such as silicates and oxalates. We believe with birches sensing these volatiles, we'll be able to support future ventures into space. After all, these volatiles will be able to aid said future ventures in everything from creating rocket fuel on site at a lunar base to creating drinkable water or even breathable air. Birches has a 4-sided iris, which will allow it to maintain a spot size and a 0.6 to 6 degrees field of view, which will allow it to maintain a sufficient footprint over the moon. We chose birches for our CubeSat because it was specially designed for CubeSats, taking up only 1.5 units, weighing 2 kilograms, and taking up 5 watts of our allotted 10 watts of power.
In order to get really accurate and precise data from birches, we had to prevent any interference from the heat of the molecules on the surface that would generate extra current or dark current. In order to do this, we had to cool the whole plate and the detector down to really cold temperatures. The BioSentinel satellite can cool the temperature to about the average temperature of a human, or 300 degrees Kelvin-ish. And so our instrument had an extra cryocooler system that can cool it down to about 110 degrees Kelvin, which is over a negative 150 degrees Celsius. Bird.
In addition to birches, we added the Chameleon Imager as a secondary instrument on our payload. This instrument benefits our mission because it captures high-quality multispectral images from the height of our proposed lunar orbit. Chameleon, when used in conjunction with birches, will provide us with a visual, allow us to distinguish the location, and ultimately help us map various volatiles on the lunar surface. The camera has a mass of 1.35 kilograms, consumes less than 3.5 watts, and takes up a total of 2 units on our 6-unit CubeSat. Moreover, the camera comes with an additional 126 gigabytes of data storage solely for its images. Overall, its compact size and low power consumption makes it an ideal candidate for our CubeSat mission.
Alright, so after we finish collecting data with our 2 sensors, the next step in our LoveSat design is to transmit this data back to our receivers on Earth. So as of now, in the Ames BioSentinel bus, we have 2 low-gain antennas and 1 medium-gain antenna. However, because the location of the Earth will be changing constantly over the lifetime of our mission, and we will be maintaining a constant orbit and orientation, it is important that we try to find a different way to communicate, because what we have now doesn't allow us to pinpoint the Earth effectively. In order to do this and overcome this obstacle, we plan to replace the existing antennas with 1 medium-gain maneuverable horn antenna, which will transmit in the X-band frequency. By doing this, we can shift the antenna in whichever direction the Earth is and best transmit our data. On Earth, we will be receiving the data using a 12-meter US Navy Academy satellite dish with similar-sized antennas, as well as similar-sized antennas in the near-Earth's space network. This will allow us to send data down to Earth at a rate of 8 kilobytes per second and receive data from these transmitters at a rate of 1 kilobyte per second. And with these rates, we are allowed to transmit 4 to 5 images from our Chameleon sensor and all of our spectrometer data per orbit during our transmission stage. And after reviewing the many factors that can affect our communication system, we believe that this setup will allow us to best communicate and relay data efficiently. And so after we created our design, the next step was to ensure that since we are sending data over long distances, we need to be able to be sure that our data can be heard back on Earth. So in order to do that, we created a link budget calculation, which, to put simply, a link budget calculation is a method of evaluating the factors which can benefit and harm data transmission. And they can help to ensure that our receivers and transmitters are sufficient for our mission. For example, factors such as power, bitrate, and antenna gain all improve our ability to communicate, whereas noise, power density, and distance can diminish our signal. And so all these factors come together to generate our expected received signal to noise ratio, which is at the bottom in the blue. It says E and O. So all of those factors come together to create that final variable. And so for a reliable comm system, we expect to have at least 10 or more decibels for this expected signal to noise ratio. And after doing our calculations, we found that we had a ratio of about 4.987 decibels, meaning that we can transmit data without complications. Next, onto the power systems. Ames provided us with 6 3.6 volt battery cells called the Panasonic NCR 18650B batteries. And together, these batteries provide the entire CubeSat with 60 watts of energy, which are purposed towards BioSentinel systems and our payload. Unfortunately, a majority of this power goes towards the BioSentinel systems, and our payload in our 4 units is left with only 10 watts. And this becomes problematic because our Chameleon sensor and our Burgess sensor use 3.5 and 7 watts respectively, meaning we would exceed the 10 watt limit. And because we did have extra space, we decided to include an additional Panasonic battery, which would give us an additional 10 watts of energy to purpose towards our payload. And because our solar panels are always oriented in the direction of the sun, we wouldn't have any issues charging these batteries, and we would be able to get the most out of them. And so, with this additional battery, we wouldn't have to alternate the use of our instruments every time we orbited. If we were to have to alternate our instruments, we would halve the amount of data that we could collect over the lifetime of our mission. Instead, this slight alteration allows us to use both of our sensors simultaneously each time we cross the South Pole, and allows us to get a more detailed image of what the South Pole and the lunar surface might look like.
So our proposed 15-day mission begins with LoveSat being placed in an elliptical lunar orbit by NASA Ames. As Sarah stated earlier, we chose to conduct our mission surrounding the full moon phase because it provides the best exposure for both the solar panels and the Earth-facing antenna. The first phase of the mission is instrument testing. The satellite will conduct 5 days of testing, including deploying its solar panels, calibrating the data stream, and ensuring that all of its instruments are working properly. After all testing is complete, the CubeSat begins collecting data. Over the course of 10 days, the instruments on board will work together to sense and map the composition, volume, and density of lunar volatiles, including water, hydrogen sulfide, ammonia, carbon dioxide, methane, and hydroxide, all on the south pole of the moon. As we examine the mission more closely, we see that the satellite will collect data from a height of 100 kilometers above the lunar south pole, and while it is moving at a speed of 1.78 kilometers per second. During this part of the orbit, the instruments on board will sense data for 12 minutes with a field of view of approximately 6 degrees. After LoveSat leaves the South Pole, it will transmit data back to Earth using its medium gain antenna, as well as recharge its systems using its solar panels. Altogether, LoveSat will spend 12 minutes of every 164-minute orbital period sensing volatiles. We expect our satellite to achieve about 100 passes over the lunar South Pole, collecting about 19.5 hours of data during the official 15-day mission.
So now that we've discussed the mission as a whole, what we have to evaluate is the real-world application of this satellite. We had to make a lot of assumptions during this project, mostly because of our time constraints and because of the calculations we had to do. Now, looking at the real world, an important evaluation to make is the cost versus the scientific gains of this mission. CubeSats are generally chosen because of their low cost in manufacturing and deployability, but we would still need to find funding somehow, so being able to justify this cost is very important. The Aerospace team believes that the data would help future explorations, although that's always debatable to some. The other important consideration we made for feasibility, and another big assumption we made, was the orbit stability. Now, this has been mentioned slightly before, but the lunar surface is extremely irregular, and there are large peaks that have gravity pulls that could pull something from a low lunar orbit. Now, our mission is only 15 days long, so we should be fine during this time, but what we have to consider is after. The fate of LoveSat is either to continue collecting data for up to a year longer than what we've expected, or it will crash into the surface of the moon and end the mission. We will achieve our goal regardless of the fate of LoveSat, but extra data would always be beneficial in trying to evaluate the effectiveness of this mission.
We chose to design a lunar orbiting volatile experiment satellite for multiple reasons. We wanted to design LoveSat to aid the development of CubeSats, since they have not been sent to the moon yet and have functioned only in low Earth orbit. LoveSat is a simple design and low cost, which could potentially aid deep space exploration missions in the future, which could revolutionize satellites in space. LoveSat could also contribute to the scientific knowledge of the early thermal history by sensing and mapping volatiles to show where and how much are trapped in the shadowed regions of the moon. Although LoveSat may be small and simple, the impact could potentially change our understanding of the moon itself.
There are some of our references. And then finally, we would like to thank all of the people who have helped us throughout our project, including NASA, NASA Ames, Dr. David Korsmeyer, Dr. James Chartres, Mr. Walter Daniel, Dr. Wallace Fowler, Mrs. Margaret Baggio, and all the SEAS internship staff for their help and support throughout the course of our project.
As a group, we thank the NASA SEAS internship for helping us to realize that our dreams can also be our realities. Our favorite part of this experience was getting to collaborate with a team of unique and brilliant individuals who all share a common passion. We are grateful to have had this experience as a stepping stone on our path to our futures and ultimately our paths to changing the world. Thank you. Any questions?
Is there anything in the box?
Oh, no, there's nothing in this box. This is just it gives an example of size with how small it is. Yeah.
This
Full size.
And this one's 1/3 scale. Yeah, it's very small space.
We have a question.
Yes.
Can you say just a little bit more about your crowd generator, how that code generator works?
What do you mean?
Explain more about the cryocooler.
So the cryocooler system, the Biosentinel spacecraft comes with its own cryocooling system that can cool the temperature of the spacecraft maintain the temperature between 0 and 50 degrees Celsius. But for our sensors, we needed to have a additional cryo cooling system to prevent any interference as the molecules move around just by the thermal energy. And so our cryo cooling system comes with a Birch's instrument. And so it's no additional weight. It's attached to the instrument itself. But it's specially designed in order to cool the instrument to sub-zero temperatures to prevent any interference.
Okay, so you're just buying this and assuming it works?
Yes.
Yes, most CubeSats, it is their databases where you just purchase parts that are pre-existing and customize the CubeSat to what you want it to discover.
Thank you.
Any other questions?
I think we got a time constraint here.
Please join me for thanking the Aerospace.